Up here. After we start lecture, no more quiz 1s, quiz 2s will be accepted. And a reminder, SQ1, which you can now tackle successfully, I hope, is due Monday. Start a class. Got to keep you busy. I didn't synthesize this 6-week gathering, but I do have the responsibility of running it. And running it we shall. That's the right place? So we proceed with chapter 19. To reiterate, first off, in chapter 19, we asked you to learn the definition of a new K, specifically KSP. So now, in our grab bag of Ks, we got, in addition to KW, KA, KB, and now KSP. At the end of chapter 19, we'll introduce you to the remaining type of K that you have to consider in chemistry. KF, where the F stands for formation, or some authors look at it as KD, where D is dissociation, where we will talk about the reaction of component species in solution to form a complex ion. Or, if you take the KD approach, you're looking at the equilibrium constant for the reaction in which the complex ion dissociates into its component particles in aqueous solution. After that, that's it. No more other K's to be considered in chemistry. Now, part A, chapter 19. Immediately after introducing you to the definition of KSP, then you start the simplest possible solubility calculations, given that the most common calculation which we do for a solution saturated with a semi-soluble salt is to get the solubility of that salt determined. In addition to this, still with part A. And for part A, this calculation is simple, because you need only do arithmetic with the KSP expression. Why is that true? Because neither component ion of the semi-soluble salt, which falls in the category A, is an ion which exhibits any Bronsted-Lowry acid-base properties of consequence in water solution. So there's no BLAB reaction to pay attention to, no hydrolysis. What does hydrolysis mean? Reaction with water, that's all hydrolysis means. So Ka, if you want, you can look at it as a hydrolysis reaction. Isn't that a reaction with water? Yup. Kb, the same thing. And the first example, which you took a look at when you started chapter 19, was the solubility for silver chloride. Chloride ion, as you know, is the conjugate base of a strong acid, HCl, and exhibits no impact on pH in water solution. How about silver ion? Presumably you talked about this in discussion class on yesterday. If you're in the lab, and I issue the responsibility, I assign you the task of proving that silver ion in water solution, because all positive ions hydrate. The question is, does the positive ion, like any metal cation, does it hydrate with sufficient strength as to A, form a well-defined hydrate, and B, a well-defined hydrate which will behave as a Bronsted acid? Okay. If you take aluminum nitrate solution, for example, or aluminum chloride solution, which you deal with in lab. Hey, By now, I expect you've all done this work in Assignment 4. I expect you're in Assignment 4. If you take and observe the pH, for example, for 10th molar aluminum nitrate solution, you'll get a pH that's about the same as 10th molar acetic acid. That shouldn't surprise you, given that the acid-base table shows you that Ka aluminum ion, hydrated aluminum ion, Ka acetic acid are about the same. Acetic acid 1.8 times 10 to the minus 5, hydrated aluminum ion 1.4 times 10 to the minus 5. I'm reading this information right off the table, given that I see this table all the time. As I said, it's a pleasurable view for me. Don't worry about it. If you ever get in a position where you do this stuff as I'm doing, you'll see the table as well. And with it, you'll have happy dreams. But what about silver ion? Again, silver ion, cation, it's got to form a hydrate. Is it a well-defined hydrate? Indeed it is for silver ion. Studies show that the formula for hydrated silver ion is this simple hydrate. It's a dihydrate. Most metal ions hydrate to form octahedral complex ions. These hexahydrates that we have on our table, most of them are octahedral. Now hexaquo copper plus 2, which you see in the table, is not a perfect octahedron. You know what octahedron looks like? Central atom or ion species here, surrounded by a square arrangement of 1, 2, 3, 4 peripheral atoms or groups bonded to the central atom, and one on top and one down below. And if they're all the same groups, like for hexaquo aluminum plus 3, it's a good bet the species is octahedral. Hexaquo aluminum plus 3 is a perfect octahedron. Hydrated copper ion, which is also a hexahydrate, is not a perfect octahedron. It's close to being an octahedron, but it's a distorted octahedron because the axial water molecules are farther away from the copper ion than are the in-plane square-arranged water molecules. Because of a novel chemistry shown by species like copper ion, referred to as the Jahn-Teller distortion. And if we had time in chapter 24 to talk about this, I'd show you where this comes from. It's not difficult. It's just, again, something you haven't heard of before. So if I start talking about Jahn-Teller distortion, your first reaction would likely be, what the hell is that? It's okay, I understand that. It's the way I reacted when I heard this stuff the first time. It has to do with the fact that copper ion, in its valence environment, has an uneven valence d electron configuration. It's a D9 ion. That leads to this Jahn-Teller distortion. And some good stories go along with it, which serve to validate the ideas we have about orbitals. But that's just talk on the side. That doesn't mean anything what we're doing now. Okay? Back to hydrated silver ion. What do you think the geometry is of that thing? Make a guess. Here's the metal ion in the center, and it's got two groups peripheral to it. Two water molecules. Okay? Do you recognize that this is, in essence, a three-component species? The silver ion in the center, and a water molecule, and another water molecule. And when you have such a species, there are only two possible geometries it can exhibit. What are the possible geometries? Linear or angular or bent. That's it. What do you think this one is? Just for fun. It's linear. That's okay. We're not in position to talk about that now. But if we get to this in chapter 24a, you'll find out it's easy to recognize that this thing is a linear species, because I will show you, if we get there, how to apply the fundamentals of hybrid theory to this thing, which will reveal that this is an sp hybridized silver ion. sp. You associate 180-degree bond angles with sp hybridization? Enough said. But that part's just for fun. We're back to the laboratory. We're searching for a solution that has a high concentration of silver ion. The only one you have available in the laboratory is silver nitrate solution, because silver nitrate is one of the few highly water-soluble salts of silver ion. Silver ion is a very interesting ion. Only got a charge of +1. But have you already caused to recognize that silver ion is a pretty doggone reactive thing? Why do you say so? The positive charge density of sodium ion compares how to the positive charge density of chloride ion. Silver ion. Na plus versus Ag plus. Which has the higher positive charge density? Which one? They're both +1. So the one with the higher positive charge density is the ion which is smaller. Well, which one is smaller? Na plus, which is isoelectronic with neon, its nearest neighbor, noble gas. I like the way that rolls along. Okay. Oh, here's silver ion, derived from silver, way down here in period number 5. If you could see a silver ion all by itself, and a sodium ion all by itself, each would be spherical entities. Simple monatomic spherical entities. But which one would be larger? Silver ion, a good deal larger, and it is. Measurements serve to establish that. Yet it is a far more reactive ion than sodium ion. Far more reactive. Nay. Sodium chloride, readily soluble in water. How about silver chloride? They're readily soluble in water? Hell no, you know this from laboratory, right? Isn't that the way, for example, you learn to test for chloride ion in assignment 2? Treat a solution suspected to contain chloride ion, first with hydronium ion to make the solution as acidic, and second with a source of silver ion. And wham, if this white milky precipitate comes out, you got silver chloride. Silver ion also precipitates with hydroxide ion to make silver oxide. It precipitates with carbonate ion to make silver carbonate. Precipitates with a source of sulfide ion to make silver sulfide, which is a damn stable stuff. You remember talking about silver sulfide in the equilibrium game that you were programmed to play? How to calculate K values for complex equilibrium? Don't you think it's funny that silver ion with a much lower positive charge density than sodium ion is a far more reactive ion than sodium ion? Don't you think it's unusual? I mean, if you're interested in chemistry, I should think at a glance you'd say, something's awful funny going on here. I'll tell you what the funny depends on, or where it arises from. Silver ion is a transition metal ion. Silver ion has an abundance of valence electrons, whereas sodium ion has 0 valence electrons, which is, practically speaking, why sodium ion, in reacting, forms compounds which are, for the most part, strictly ionic in character. Ion-ion bonds, but not silver ion. Most chemistry shown by silver ion involves the conversion of silver ion, even though it's reacting with a negative ion. Like hydrogen sulfide ion to make silver sulfide. Okay? Silver ion loses its ionic character in this reaction. Silver ion, in essence, converts back to silver atom. Silver sulfide is notoriously covalent in character. Did you learn in 2045? I keep asking these questions, what you learned in 2045. Maybe we'll find out sooner or later that you got something. Okay? How's the strength of a covalent bond compared to that of an ionic bond in general? Which is stronger? Oh, no, it isn't. The strongest bond is covalent. You betcha. Do you find that many ionic compounds have their ionic bonds broken when they're stirred in the water? Right? Sodium chloride, all these ionic compounds which dissolve in water are dissociating. The ionic bonds are breaking apart. There's not many molecules which, when they are dissolved in water, have their covalent bonds torn apart. Not many. In any case, more on that later. Back to this. I get involved in these chemistries. Somebody said to me before this term, how can you handle 5 75-minute classes during the week for this 6-week thing? I said, guess what? I can lecture 5 hours a day, 7 days a week, for 10 weeks. And then I'll show you a bunch of chemistry. And the only thing which I would be caused to be concerned about is exhaustion. You as well as me. So I wouldn't run a class like that. But believe me, I got the material to run a class like that. And every one of you have sufficient intelligence capacity to digest the stuff that I would present. And I mean to tell you what, when you were to walk away from that gathering and you walked into any subsequent chemistry course, be a piece of cake. That's right. And that's what I want. I want you to leave this course and go into organic and tear it apart. Because you'll have the tools to be able to digest it. Analytical, the same stuff. PChem, it all works. Fundamental inorganic chemistry, hell. I've had inorganic graduate students teaching for me who say, some of the inorganic graduate students, when they take cumulative exams upon which earning the PhD depends, they're not as tough as my exams. Hey, but you've been programmed to deal with this stuff. By me. That's my job. That's what I love doing. In any case, forget all that for now. Back to this. You get this silver nitrate solution because it's the only solution in lab which has got a high molarity of silver ion. You know that nitrate ion in the solution can't have any effect on pH because nitrate ion, like chloride ion, is the conjugate base of a strong acid, right? So what measurement would you make of silver nitrate solution to prove that hydrated silver ion shows no effect to speak of on solution pH? What measurement would you make on silver nitrate solution to prove that that ion is not showing any effect of consequence on pH in water solution? You got this silver nitrate solution before you. We used to use 10th molar, but now we're down to 200th molar. That's okay. The lower the molarity, the greater the ionization extent. What measurement would you make on the silver nitrate solution? You're trying to find out, does that ion, yes or no, exert a measurable effect on water solution pH? You'd measure pH, wouldn't you? And if it's the same as solvent water, boom, that's it. Game over. Right? That means the presence of silver ion in that solution is not changing the pH relative to that which is shown by solvent water itself. And that's what you find out. So now we're just giving you an idea of how you would pursue these tasks in laboratory, because this is a lab science. Everything has to be confirmed by experiment. I mean, I can provide the most elegant, wonderful sounding explanations. But if the experimental results don't keep with my explanations, I damn well better change my explanations. Because the experimental results aren't going to change if the experiments don't be done properly. Because molecules and ions, bless their wonderful souls, don't give a damn what I say or what I think. Never have and never will. They don't care what calculations I do. They don't care what theories I cook up. They never have and they never will. Now, can I take action that will affect how ions and molecules behave? Absolutely. Blow off a hydrogen bomb around them and by golly, you'll change how they behave. But ideas, thoughts, words, theories, calculations, that doesn't change how they behave. All right. And now we're at this. A more challenging issue regarding determination of solution properties like solubility and pH. pH. Does it sound like being able to understand what's going on in chapter 19 rests rather heavily on what we have just finished doing in chapter 18? How about that? That's why we go through this chapter 18 stuff in great detail before we get to this stuff. You'll find the same thing when we get to electrochemistry. It depends heavily on Bronsted-Lowry acid-base chemistry. Heavily. Complex ion formation depends heavily on Bronsted-Lowry acid-base chemistry, and also on Lewis acid-base chemistry, which we will begin to discuss at the end of this chapter. In sum, then, calculating solubility for a semi-soluble salt, which falls in category B, is much more challenging than that which is in category A. Because now at least two equilibria have to be considered. KSP and KB. Well, the two equilibria which have to be considered. And if we're dealing with particularly dilute solutions, whatever have you, then we might need to think about KW. Who knows? As our adventure continues into chapter 19, we'll find out. Now then, question 19.3 is in regard to my issuing to you this directive. Because students want to do this all the time. They look at this information sheet, which contains a slew of semi-soluble salts, right here, and their corresponding KSP values. You see that? Do not make decisions on salt solubilities directly from KSPs. Do not say that this salt has a lower KSP than that salt, therefore the salt with the lower KSP is less soluble. That's dead wrong in more cases than you will be right. Don't do that. You want to compare solubilities? There's only one way to do it. Calculate the solubilities. Then you can compare the solubilities. Don't make the comparison of solubility on the basis of KSP. Simple illustration. The illustration is on the board. It involves two salts, which from a solubility standpoint fall into category A. Because fluoride ion and oxalate ion are pretty weak Bronsted bases. If you take and make saturated calcium fluoride solution, you'll find out that its pH is about the same as that as deionized water solvent. Same for this solution. Now, how do their solubilities compare? This stuff is less soluble, the calcium oxalate is less soluble than calcium fluoride. But this stuff, the calcium fluoride with this solubility value is about twice as soluble as this. But look at the KSPs. Here's KSP for calcium oxalate. Here's KSP for calcium fluoride. Hey, this is a much smaller number than that. So if you look at this much smaller KSP value and say that means this stuff is less soluble than this, you are dead wrong. And you've already learned how to do the arithmetic to get at this. I've shown you here the arithmetic. KSP this, since no hydrolysis, is square root of KSP. Solubility of this, given that we have no hydrolysis to be concerned about, is square root of KSP. Here, solubility is the cube root of KSP divided by 4. Just write out this calcium fluoride equilibrium reaction in water, right? So the equilibrium molarities of the component ions are S and 2S. And the KSP expression is calcium ion molarity times fluoride ion molarity squared. So algebraically, KSP is S for calcium ion and 2S quantity squared for fluoride ion. Well, that's where the 4S cubed comes from. Okay? And that's where this result comes from to get solubility calculated. Enough on that. Let's proceed with subcategory B considerations. And for many of the subcategory B considerations, we will use as our exemplary semi-soluble material, teacher's favorite weapon, calcium carbonate. Consideration number 1. The experimentally determined molarity for calcium carbonate at NLC, normal lab conditions, reveals a solubility value at NLC of 1.4 times 10 to the minus 4 molar. Okay? Now remember, or note that, calcium carbonate in one respect is like silver chloride. Silver chloride has a stoichiometry that's 1 to 1. Or like calcium oxalate, right? 1 to 1. Per mole of silver chloride, you got a mole of silver ion, mole of chloride ion. Per mole of calcium carbonate, you got a mole of calcium ion, mole of carbonate ion, right? That's what I mean when I say 1 to 1. Okay? Like calcium oxalate. Not so for calcium fluoride, right? Because per mole of calcium ion and calcium fluoride, you got 2 moles of fluoride ion. So stoichiometrically speaking, calcium fluoride is different from these other 3 semi-soluble salts. So if calcium carbonate, on dissolving in water, showed this chemistry only, we know it shows this chemistry because that's dissociation. So we know this chemistry is shown when calcium carbonate dissolves in water. But is that the only chemistry which calcium carbonate shows when it dissolves in water? Because if that was the case, then the solubility of calcium carbonate would be determinable like the solubility of silver chloride, square root of KSP. Well, a KSP value of 6.2 times 10 to the minus 9. Pulling it right off the table. Take the square root, I get 7.9 times 10 to the minus 5. And this thing is about half of the true solubility. So clearly, square root of calcium carbonate KSP hardly gives us an accurate, reliable value for solubility. So something else is going on. Something is driving the solubility to be considerably greater than the solubility calculated by square root of KSP. Yet today, I still see a number of general chemistry textbooks which will take the square root of KSP for calcium carbonate and call that its solubility. Flunk! What good is that? I mean, you can keep the arithmetic as simple as possible, but if it doesn't keep with facts, what good is the arithmetic? Indeed, carbonate must be considered, which we showed back in class day number 1 and yesterday. Remember we made the calcium carbonate saturated solution, put some phenolphthalein in there, got the distinct red-pink, showing us that on dissolving calcium carbonate in water, we get a solution which is distinctly basic. So it follows that in saturated calcium carbonate solution, that the solubility is equal to the calcium ion molarity if this thing, because calcium ion does form a well-defined octahedral hydrate, okay? But if that thing, hydrated calcium ion, shows no Bronsted acidity of consequence, then after calcium ion is put in the solution by dissolving calcium carbonate, calcium ion just sits there. So whatever the solubility is of calcium carbonate is equal to the equilibrium molarity of calcium ion. How would you find this out? How would you find out whether or not in water solution you have to pay attention to the Bronsted acidity of hydrated calcium ion? What do we talk about regarding the silver ion? Let's do the same kind of thing with calcium ion. Let's go to the laboratory and get your lab solution of calcium chloride or calcium nitrate. Who cares? Both are salts with a negative ion that exhibits no impact on pH. And so if I observe the pH of half molar calcium nitrate solution, half molar calcium chloride solution, and I find the pH is the same as DIW, Is this hydrated calcium ion doing anything? Absolutely not. And that's just what you'd find out. Aha! But if I take the calcium carbonate saturated solution, as we have already demonstrated, and observe pH, I find a system which is considerably basic. So I know right off the bat, carbonate ion isn't just sitting there when I put it in solution. It's doing something else. It's behaving as a Bronsted base. Is this surprising to us, given the information we've gotten from Chapter 18? Is it surprising to us after we look at our acid-base table and see in the base column, carbonate ion is a weak base but of appreciable strength? It's near the bottom of the base column. See carbonate ion down there? Got a Kb value of 2.1 times 10 to the minus 4. Right. That's why we got this pH that's considerably greater than 7.0. Okay? So at equilibrium in calcium carbonate solution, the initial molarity of carbonate ion, that's how the molarity of carbonate ion established by dissociation. But the initial molarity of carbonate ion is hardly the same as its equilibrium molarity, because carbonate ion then goes on to react with water and establish this equilibrium. And of course, the K value for this equilibrium is by definition Kb carbonate. This we already know. Chapter 18. Okay? Now then, if we took our saturated calcium carbonate solution and measured pH by the methods you have available in laboratory. How many of you have done this in assignment 3 already? Because I expect you're there. What value did you get? pH for saturated calcium carbonate solution. What value did you get? Many of you indicated you've already done this. Do you not remember the value you got? How can you do this and it doesn't sink in? I don't get that. I mean, it can't be that far away. I mean, when you've done this, within a few days, a week. And nobody who's done this work remembers what the pH for saturated calcium carbonate solution is. It's about 10. Is that what you got? Wonderful. Hey, you know how I am. Any work that you've done in 46L, I expect you to know. Period. End of story. Because it provides foundation for this gathering. Is that rotten and nasty and too demanding of me? I don't give a damn. That's the way you got to behave if you're going to learn chemistry. It's too tough to go about it in any other fashion. So, upshot of this, equilibrium molarity of calcium ion in saturated calcium carbonate solution is a good deal greater than the equilibrium molarity of carbonate ion, unless we have done something to the calcium carbonate saturated solution system which stops that equilibrium reaction in its tracks. How might we do that? If you want to dissolve calcium carbonate in water solution and have the calcium ion and carbonate ion equilibriums be equal, what conditions must you establish for this solution? Can we achieve that? I'm now going to set you free in 46L. I'm going to give you some calcium carbonate. I'm going to let you use any of the reagents that are in there, the solutions which are on the side shelf. In what solution might you consider dissolving calcium carbonate with all of the solutions being water soluble? In what solution might you consider dissolving calcium carbonate to keep the calcium ion and carbonate ion molarities equal in the resulting solution? There's the equilibrium reaction you have to interfere with.
Sodium hydroxide?
What is it?
Sodium hydroxide?
Yes! Sodium hydroxide solution. Remember? We've done this. We did this in chapter 17. Put it to use. If this equilibrium reaction is alive and well in a beaker or flask before you, and you hit that system with hydroxide ion, wham, you're going to make this reaction go right to left as written. Which means you're going back to carbonate ion. Which means you're standing in the way of carbonate ion's ability to react with water and hydrolyze and convert to those products. And one of the questions I will ask you to consider, not today, but next week for sure, is what pH do you need to stop carbonate ion? It's not a hard calculation, but we have not yet laid sufficient foundation for your being able to do this. Actually, we have, but I'll not be overly demanding at this immediate moment. I'll wait 10 minutes. How's that? On we go. KB expression here, arithmetic based on a pH of about 10, which is what you folks got in laboratory, which I'll write to 1 sig fig, 1 times 10 to the minus 4 for hydroxide ion molarity at a pH 10. And the stoichiometry of this reaction, since there's no additional source of either of these ions other than this reaction, these molarities will be equal, so they'll each be 1 times 10 to the minus 10. S is the initial molarity of carbonate ion. And the equilibrium molarity of carbonate ion is S, less the molarity of a derived species. Isn't that material balance applied to carbonate ion? You betcha. And there's the derived species. 1 times 10 to the minus 4. So I do this arithmetic, I get 1.5 times 10 to the minus 4 if I cheat on sig figs. Hey, that's not bad. Our experimentally measured value, the 2 sig figs, is 1.4 times 10 to the minus 4. So this is ever slightly greater than the true solubility. Ever slightly greater. That tells me that the true pH for saturated calcium carbonate solution, remember you reported about 10, and that's to 1 sig fig, the saturated solution pH of calcium carbonate is in fact 10.0, because 10 itself is no sig figs, because that's a log. 10.0. And that's the true pH of saturated calcium carbonate solution. But given that we know the true solubility is 1.4 times 10 to the minus 4, and this gee whiz approximation based on a pH of 10 gives us 1.5 times 10 to the minus 4. Okay. If I take the pH for saturated calcium carbonate solution to 2 sig figs, which would require that you use the pH meter tuned up in the lab to observe. Okay. Well, I find the true pH to be greater or smaller than 10.00, because now I'm talking about pH to 2 sig figs. Well, I find the true pH to be greater or smaller than 10.00. Given that, the true solubility is a little bit smaller than this gee whiz solubility determined on the basis of pH 10. The 2 sig figs is the true pH for saturated calcium carbonate solution, bigger or smaller than 10.00. The true pH is smaller. Smaller is correct. Now, of course, how do you know that? That's the question. That's the question I want you to answer. How do you know that? Well, keep that in your mind's eye for a moment, because we'll be at an issue which is immediately parallel in just a moment or two. In any case, if then we wish to approximate the extent to which carbonate ion has converted to bicarb ion by this reaction, based on pH 10, here's what we get. 67%. Now, what I have to do, if I want the true percent hydrolysis, is to get the hydroxide ion concentration that corresponds to the true pH of 9.95. Pretty close to 10.00. Okay? Divided by the true solubility. And if I do this, I get 70% more or less. So, my golly, this carbonate ion is going away substantially, isn't it? When I make my saturated calcium carbonate solution. It's becoming this and serves to produce this on the order of 70%. Which now, from an arithmetic standpoint, accounts for why I cannot get a handle on the solubility of a material like calcium carbonate from square root of KSP. That gives me a value which is ridiculous. Okay? So now, yes. Take a look, if you will, at question 19.7. We know this, and we're now in the lab with a different semi-soluble carbonate. A different semi-soluble carbonate, which in one respect is similar to calcium ion. What is that respect? How is this metal ion similar to calcium ion? If the formula is MCO3. It's +2, just like calcium ion. But saturated solution for MCO3 shows an observed pH of 11.0. Considerably more basic than the saturated calcium carbonate solution. So here's the $64 question. Shorthand for soluble. Solly. I'm not Solly. I carry on with this all the time. Which is more Solly? Is it M carbonate or calcium carbonate? You've got all the information you need to answer this question. M carbonate is more soluble. I have votes here in that regard. You who have not voted, how many would like to support the contention that M carbonate is more soluble? Well then, for the non-voters, I'm assuming you vote that calcium carbonate is more soluble. And you're wrong! Because M carbonate is more soluble. Now defend that statement. How do I know for sure M carbonate is more soluble? What is that?
To get a more basic solution, you produce more hydroxide.
No, don't say more. I mean, it will be more on a liter basis.
A higher concentration.
Yes!
To do that, you need to give more.
There has to be a greater solubility shown by this stuff than this stuff. Because in each case, the observed pHs are attributable to carbonate ion hydrolysis. Okay so far? Okay? Now then, if I go to the laboratory, and I issue to you a solution for which the initial molarity of carbonate ion is 1,000th molar. Initial molarity. Because we already know it's going to hydrolyze. Versus a second solution for which the initial molarity of carbonated ion is 10,000th molar. Okay, these are the two solutions. Those are the initial molarities. Now, this solution is considerably more dilute by a factor of 10 than this solution. So in this solution, percent or extent of hydrolysis of carbonated ion is what? Smaller or greater? Greater. But which of these solutions has the higher hydroxide ion concentration? Don't look mystified by this. You did work to support your answer in laboratory. 1 molar acetic acid solution, 10th molar acetic acid solution, right? Clearly, the ionization extent of acetic acid in 10th molar solution exceeds that in 1 molar. Which solution is more acidic? The more concentrated solution is always more acidic. You can't get something for nothing. It can't be. That carbonate solution has got to be more basic than this carbonate solution because it's got a higher initial molarity of carbonate ion. It's got a higher molarity initially of the stuff that makes hydroxide ion. So the higher the initial molarity of the stuff that makes hydroxide ion, the greater the pH, higher the pH, right? And here, on a per liter basis, I'm making more hydroxide ion. That means this stuff has got to be more soluble. The initial molarity of carbonate ion in this stuff has got to be higher than the initial molarity of carbonate ion in this stuff. Okay? Now, if you take what we have just stated and the thinking which underlies what we've just stated and applies it to here, you'll recognize why that at a true solubility of 1.4 times 10 to minus 4, right? Versus the gee whiz solubility of 1.5 times 10 to minus 4. Hydroxide ion molarity in the true solution has got to be smaller than the hydroxide ion molarity there. Okay? Which means pH has got to be lower than 10. And on we go. Now we're in the laboratory, again, this time observing pH for saturated silver carbonate solution versus that for saturated silver sulfide solution. Question number 1. Based on this observed pH for saturated silver carbonate solution, how do you expect the solubility of silver carbonate, water solubility of course, to compare to that for calcium carbonate? About equal, wouldn't you say? Aren't they showing us the same pH? That means they're putting the same carbonate ion initial molarity in the pot, aren't they? So they got to have the same solubilities. Right? Hey. This is the part you got to think about. Now let's peek at the silver sulfide solution. Saturated solution pH 7.0. If you take it to do sig figs, it's 7.00. What can I say absolutely and for sure now about the solubility of silver sulfide compared to the solubility of silver carbonate? Less soluble? A little bit less soluble? Immensely less soluble. Because sulfide ion in solution hydrolyzes to what extent? What extent? Sulfide ion ionizes in water solution to what extent? 100%. It's one of our Strongy bases. Right? There's no equilibrium governing the ionization extent of sulfide ion, particularly in dilute solution. That's a 100% job. So if silver sulfide and silver carbonate had the same solubilities, which saturated solution would have the higher pH? Silver sulfide. Because if I've got an initial molarity of sulfide ion, which is greater than an initial, which is the same as an initial molarity of carbonate ion, and all the sulfide ion becomes hydroxide ion, I got to have a higher pH. Hey, this pH is 3 pH units greater than this pH. This has got a hydroxide ion molarity, which is 1,000 times greater than the hydroxide ion molarity of this solution. So what can I say then about the absolute solubility of silver sulfide in water? Because dissolving it in water, even though sulfide ion is this strong base, I haven't changed the pH relative to straight water itself, have I? So how much silver sulfide am I dissolving? How about damn near none? Because that stuff is horribly stable. And it's horribly stable because of the extreme covalent nature of silver sulfide. When silver ion and sulfide ion get together, they practically speaking lose their ionic character and become a very, very stable covalent material, substantially, extremely stable silver sulfide. Okay? When you folks get to assignment 7 in 46L, you'll make silver sulfide. You'll also make zinc sulfide and copper sulfide. And you'll discover that copper sulfide and silver sulfide cannot be dissolved effectively by hydronium ion attack. I don't care what the hydronium ion concentration is. Screaming at you, wow, are we stable? We were made from this potent base sulfide ion, but you can't do anything to us, practically speaking, with hydronium ion. And copper sulfide and silver sulfide physically look just alike. They're powdery materials, brown-black, more black than brown in color. And they show no dissolvability in water to speak of. They show no dissolvability in 12 molar hydronium ion to speak of. Well, if I give you this brown-black material, which resists attack by hydronium ion, for an unknown in assignment 9, and you can't get it in solution with 12 molar hydronium ion, you know it's copper sulfide or silver sulfide. Well, how are you going to answer? How are you going to figure out which one it is? You got to have a way to get the damn thing in solution. And that way will be revealed to you in assignment 8. Where you will learn how to supplement hydronium ion attack with oxidizer attack and murder sulfide ion by oxidizing it to something else. And that'll get the silver sulfide and the copper sulfide in solution. And when you get these in solution, you'll find out that the test tube in which you dissolve the copper sulfide will show what kind of color. Anybody recall the color shown by copper ion in solution? Blue. You betcha. Okay. But silver ion in solution? Any color for silver ion in solution? Colorless. None. That's how you'll find out. Okay. Now then. Let's start taking a look at pH-dependent considerations relating to what we have so far discussed regarding subcategory B. Gee, I bet you're surprised at that. pH-related. Chapter 18. All over again in some respects. S. For calcium carbonate in a water solution buffered at pH 8.00 And we will assume that the only function of the buffer in this solution is to maintain pH at 8.00. How will the solubility of calcium carbonate in this system compare to its solubility in deionized water, where we've already recognized that in deionized water saturated with calcium carbonate, we observe a pH of 10.0. Here we're going to have the pH remain at 8.00 because the system is buffered. How will S for calcium carbonate in this system? Compare to this number, because this is the solubility in straight water. And for that system, the pH is 10.0. How's the solubility here? Going to compare to that. Now keep your thinking caps on before you respond to this. Because the solvent is not straight water. Is this system clearly a system which is more acidic than our saturated DIW system?
Yes.
Is it not 100 times more acidic?
Yes.
pH 8 versus pH 10? 100 times more acidic. Tell me, if you wish to dissolve a carbonate material, like calcium carbonate, how would you attack it? You want to beat up calcium carbonate. You want to get it to dissolve. How will you attack it? You did this in assignment 3 in the lab. How will you attack it? Will you hit it with hydroxide ion? Will you hit it with ammonia? You hit it with deionized water straight away? Will you hit it with a weak acid? You hit it with a strong acid? How will you attack this calcium carbonate to render it soluble? What are you going to hit it with? An acid, damn right. You want to beat up bases, you hit them with acids. And this solution is 100 times more acidic than the solution obtained when straight water is saturated with calcium carbonate. So that means S calcium carbonate in this solution has got to compare how to 1.4 times 10 to the minus 4. Greater, you betcha. And that's what you got to think about before you start messing around with arithmetic. You got to pay attention to the chemistry system always. Have I said that before? You think I'll say it again? Maybe 3,000 or 4,000 times before the next 3.5 weeks expire, or 3 weeks, or whatever we got left. Okay. Now then, next question. To approach this problem, I recommend that we use this equilibrium reaction as opposed to calcium carbonate in equilibrium with calcium ion and carbonate ion. Because this equilibrium reaction does a far better job of paralleling the chemistry in this system. How can I state that flatly? Here we are in deionized water, where we got a pH of 10, right? And we found a hydrolysis extent of carbonate ion, which is 70%. 70%. So the bulk of the carbonate ion went away. Well, now we got a system buffered at pH 8. Will the carbonate ion now go away more effectively or less effectively? Isn't this system more acidic? Didn't we just talk about how you want to clobber carbonates? Hit them with acids? This system 100 times more acidic. So if carbonate ion went away 70% at pH 10, you think I don't have much carbonate ion left at pH 8? Huh? Not much. So let's use this reaction. And if I'm going to use an equilibrium reaction, I need its K value, don't I? And we know how to get K values now, don't we? There's the K expression I need to get a K value for. Now, of course, the notes show you how to do this. But without looking at the notes, we let this equilibrium reaction talk to us. Number one, we see it's got calcium carbonate, a salt of limited solubility, as a reactant. That means a component K for this equilibrium system is KSP calcium carbonate. And if I want to get KSP calcium carbonate into this, I got to play this game. And there's calcium carbonate, KSP, right? For the calcium ion molarity times the carbonate ion molarity version of calcium carbonate KSP. And I also look at this, and I remember that carbonate ion is a component ion of this, and as this reaction goes left to right, I see carbonate ion becoming bicarb ion. So what's the other component K value of this equilibrium? KB carbonate. Bingo. And when I check these off and I look at what's left, carbonate ion denominator, bicarb ion hydroxide ion numerator. Isn't that KB carbonate? Absolutely. So here we go. I better check the number, but I think that's right. You looking at it in the notes? Yeah. That it? Right? 1.3 times 10 to the minus 12? Wonderful. Okay, now then, let's make one more statement before we wrap it up for today. To approach this, since we now have the value for K, okay, we can take this part off, because this is the equilibrium constant for this reaction. We know this is S, right? That's what we want to get. And calcium ion in solution doesn't do anything further. So the calcium ion molarity will be S. What's hydroxide ion molarity? Right? There's hydroxide ion molarity. So, question is, for this system at equilibrium, how does the molarity of bicarb ion relate to S? Because as things stand, we got one equation and two unknowns. How do we proceed? We'll pick it up from this point next time.